Welcome to Spring LIB.
Hello everyone, today we're doing problem 56 out of chapter 11, and this problem asks us to synthesize each of the following compounds from acetylene, which is just your standard alkyne, 2-carbon alkyne. You can use any organic or inorganic reagent. So let's see, we want A from acetylene. So let's draw product A that we want. So we have a triple bond, carbon, and then we have 1, 2, then we have 1, 2, and then 2 carbons, 2 methyl groups coming out. So it's very obvious that we need to make this into a nucleophile to attack some sort of electrophilic component that will constitute these carbons. So we know that we need to convert this into a nucleophile. So how do we do that? Well, we take our starting material and we deprotonate one of these sig protons with, for example, sodium hydride, which we've done in the past. Now you have a carbanion that's very, very nucleophilic and very reactive towards any electrophile. So what is that electrophile going to be? Well, we need 1, 2, 3, 4 carbons. So we have 1, 2, 3, 4 carbons. Then we need a leaving group, so then something can fall off when we do the nucleophilic attack. So we'll add any halide. I'll just add bromine for the sake of this example. And then we see if we do a backside nucleophilic 180 degrees attack, SN2 attack, we will get our final product for A. And now let's see for B, what is the final product of B? So we'll do this in different colors. So we have a central alkyne, and then we have 1, 2, 3, 1, 2, 3. So it's symmetric. So we have 1, 2, 3, 1, 2, 3. So we have 3 carbons coming out on either side. So once again, we identify that the central alkyne will be our nucleophile, and we need to add now 2 sets of carbons, 3 carbon electrophiles. So just like in A, we know that the acetylene starting material will be our nucleophile by deprotonating it to make this carbanion. And now we need to add on one side these 3 carbons, so 1, 2, 3 was the leaving group, so I can use chlorine for this time. And then we'll get addition across this one side. Now we got to repeat this for the other side. So we got to deprotonate now the other side with sodium hydride. And now you get your carbanion here, and then you add the same starting material, or same reagent, sorry, because it's a symmetric molecule. 1, 2, 3. And you get your final product for B. Now let's see for C, what do we have? Well, from C we have some sort of, so this is a product for C. Let's draw it out in stick notation. It's easier to visualize it that way. So we have C in 1, 2, 3, 4. So we have 1, 2, 3, 4 carbons. So we know that acetylene will donate 2 carbons to that. So we can just say these 2 carbons are from our starting material. So we need to add 3 carbons. So just like how we added 3 carbons on this compound. So to get to C, so we have to start from our starting material. So let's do this in red. And we'll do the other 3 on another page. So this is for C. This was B. This is A. This is C. So once again, we'll start from our starting material. Remember, we know that we can add oxygens across alkenes or alkynes. So we know that the alkyne must be at this position. So we have 3 carbons in addition to this alkyne that we started with. So let's first add those 3 carbons. So this is what we did exactly in the previous example. So sodium hydride, number 1, and then number 2, we're going to add this electrophile. So now we have this, which is exactly carbon 1, carbon 2, and then these 3 carbons, which are those 3 carbons. So now we've satisfied all the number of carbons we needed. So now we need to add an alcohol to the least sterically hindered side. So we know that if we wanted to added through Markovnikov's addition, well, the rich get richer. So the side with more protons will pick up the proton. So that means that this side will pick up the proton. That means our alcohol or carbocation, which the alcohol would neutralize, would be in this carbon 2. But we know that this carbonyl aldehyde is coming off of carbon 1. So we know that we need to use a different method that adds your substituent of interest on carbon 1. So one reagent we know is boron. So remember, I like drawing BH3 as BH2 on your least sterically hindered side and H. So boron being bulky, it wants to add across to the least sterically hindered side. So you make 2 bonds, and when you make 2 bonds, you gotta break 2 bonds. So a sigma bond between the B and H will break, and one of these pi bonds will break as well from your alkyne to reduce it down to an alkene. So now you have an alkene, your 3 carbons. Now you have your BH2 on one side, and that proton on the other side. So now we know how to make this BH2 into, change it to an alcohol and then oxidize it. So there's a few reagents that you need to remember, and it's kind of beyond the scope of an introductory level organic chemistry course, but we need to add an oxidizing agent, so H2O2, and then an oxygen source, so OH minus. So this changes your boron to a carbonyl group, and then when you make a pi bond here, this bond has to break to maintain the octet rule, so the carbon will only have 4 bonds, not 5. That's how we reduce it down to an alkane. So then we're at this point now, so we add the extra 3 carbons, so we don't lose any carbons, and then we get our final product for C. So this reagent you just have to remember, to oxidize boron to a carbonyl, you need to add some sort of oxidizing agent, in this case is hydrogen peroxide, and an oxygen source being OH minus. So let's do D. So D, we're trying to get this compound from acetylene. So let's go add a new page. And we're starting with acetylene, and we're trying to get this product here. And you have 1, 2, 3 carbons. So once again, now, remember Markovnikov's addition? Well, now we're adding your substituent of interest on carbon 2, so we can do Markovnikov's addition. And we're adding those 3 extra carbons as in for B and C. So we know how to do, so let's first, just like before, let's add our carbons in first to get that out of the way. So we add sodium hydride as step 1 and 3 carbon source for step 2. So this is exactly like what we did in B and C. So remember, you always want to just add all your carbons first. So now we have our 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 carbons. Now we're adding our component of interest on carbon 2, so we can do Markovnikov's addition. So we can do Markovnikov's addition. In this case, our alcohol of choice, or our substituent of choice, is an oxygen. So let's add the oxygen source being water with some sort of acid. We can say it's H2SO4. And we know that following Markovnikov's addition, this goes to H minus, rich will get richer, so the side with more protons will pick up the proton, giving us a secondary carbocation. Remember, you pick up the proton on the least substituted side, or the side with more protons, so that your carbocation is on the most substituted side, so it's stabilized the most. So now we have a secondary carbocation, which is more stabilized than a primary carbocation. So now we have our secondary carbocation, which water can attack and neutralize. To form this enol form of the tautomer. Well, we know that through tautomerization, we can form the keto form by using one of oxygen's lone pair electrons to make a carbonyl bond. Making a bond, you make a bond, you break a bond, so the pi bond will break, going through this carbon nucleus, pick up this proton, and give those 2 electrons back to oxygen to form now the final product. And this whole reaction is also catalyzed not only by acidic water, but with mercury as well. So we should write that reagent as well. So you have to remember the trio of reagents when you want to do this keto-enol tautomerization by addition of water. So now let's see, this is D. So now let's do E. So E, we have this compound. So let's see, how would we get this compound? So let's try that out. So this is D. This is E. So E, we're going from acetylene to something that looks like this. So then we have 1, 2, 3 carbons, 1, 2, 3 carbons. So remember, it's always easy to add your substituents across an alkene or alkyne. So we know that alkyne must exist on those 2 carbons. And then we're adding 3 carbons as well. So just like in D and in C and in B, we're adding 3 carbons. So let's first do that, just like all the previous examples. So sodium hydride to make a carb anion, nucleophilic carb anion, and a 3 carbon source, an electrophilic 3 carbon source, to gain those 3 carbons. And now what we need to do is Markovnikov's addition too. But in this case, we need, on carbon 1 we have 1 proton, but in the final product we have 3. So we need to gain 2 hydrogens on carbon 1. And on carbon 2 we need to gain 2 chlorine. So we need hydrogen and we need chlorine, and we need this times 2. So we need 2 equivalents of this. So following Markovnikov's addition, we know that the richer will get richer, so the side with more protons will pick up this proton. And the reason for that is you get a secondary carbocation, which a chloride anion can attack to form 1, 2, 3, to form this product, which is using 1 equivalent, but then we do this again to get 2 equivalents, as in the products. 1, 2, 3. That's how you get E. And now F. So let's see what we have in F. Okay, so in F, we are using essentially, we have 1, 2, 3, 1, 2, 3, and then we have 2 central carbons. So this looks like very similar to the product of B. So it looks like we form the product B, and then we add some sort of oxidizing agent to add water and reduce that alcohol, or sorry, oxidize that alcohol to a carbonyl group from this alkyne. So let's use the product from B, because we have the same number of carbons. We have 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have the same number of carbons as in B, but now we're doing a little bit more chemistry to get this extra oxygen, central oxygen. So now let's do F. So remember, you always should add your carbons first. So like we've done in all the past examples. So this adds the 3 carbons on one side, and we're going to do it again for the other side, just like in B. So now we have the product in B, but now we need to add an oxygen. So if you guys see, we need to add an oxygen here. So what's source of oxygen? Well, we can add water. So let's add water. But then remember, when we add water, we get this alcohol, and then we can do keto-enol tautomerization to get your carbonyl group here. But you need to add mercury as a reagent for this trio. So we can add those same exact reagents as in D. And mercury. So remember, you're going from your alkyne as we did in D, and you're adding water through Markovnikov's addition, and then you're making an alcohol which can go through keto-enol tautomerization to get your carbonyl right there. And it doesn't really matter, even though these are equivalent carbons, there's no protons on them. So regardless of the oxygen attaches on the left or right, you will still get your same product because of the internal plane of symmetry from your starting material.